Hello, and welcome to our live stream. I'm Lusine Sukiasyan, and I work here at Wolfram Research in the Discrete Computation team, and today I'm going to present you with an overview of number theory. I'm going to talk about number theory, number theoretic functions, number theoretic capabilities in the Wolfram language. So let's begin. So, number theory. What is number theory, first of all? Number theory is one of the oldest and most intuitive fields of mathematics. It studies integers and their properties. It is called sometimes arithmetic or higher arithmetic. So, as a very famous mathematician, Carl Friedrich Gauss once said, mathematics is the queen of sciences and arithmetic is the queen of mathematics. So Wolfram language draws on almost every major result in number theory, packing a large number of sophisticated algorithms, many recent and original, into a powerful collection of functions. It's been a key tool for 2 decades in the advance of the field, and Wolfram language's symbolic architecture and web of highly efficient algorithms make it a unique platform for number theoretic experiments, discoveries, and proofs. As I said, today I'm going to talk about number theoretic functions in the Wolfram language, and we grouped them in the following categories: factoring and primes, divisibility and divisors, congruences and modular arithmetic, number representations, Diophantine and other equations, analytic number theory, and algebraic number theory. I mean, we will talk about the most basic functions, the most important, the most well-known functions, because that's the time we have. We can talk about each of these categories, if you'd like, for hours and hours. But today we're going to just give you the basics, and we will post a notebook and the links will be there. You can just go and explore this wide range of functions. So let's begin. Let's begin with the first group of functions, which is about factoring and primes. I mean, if you hear the word number theory, that's what comes to your mind. Probably the first is prime numbers. I mean, the primes have been a focal point for investigation of numbers for more than 2 millennia. And let's just start with this beautiful quotation by Paul Erdos, who said, "God may not play dice with the universe, but something strange is going on with the prime numbers." So Wolfram language implements the modern algorithms for handling both primes and the advanced mathematics that has grown up around their study. And these functions, again, we grouped all the functions concerning factoring and primes into the following categories: generating primes, sequence of primes, primality testing, theorems, and equations. Let's begin with generating primes. And here, of course, the basic function is the function prime, which gives you the nth prime number. For example, you can use it to quickly find the millionth prime. And here you go, this is the millionth prime. Or the next function is the function next prime, which gives you the smallest prime above x. So you can find the next prime after 1000 by simply doing next prime 1000. Or you can visualize the gaps between primes below, say, 10 to the power of 4, and get this nice visualization by doing next prime s and next prime s minus 1. So, as I said, next prime 1000 gave you the next prime after 1000, and the next prime 1000 minus 1, what does it give you? It gives you the prime just before 1000. All of these functions that we're talking about today, they have their different kind of verifications. You can go check them, the reference pages. We have the links. We won't go in details, but yeah, all the functions have different verifications, modifications. But we're only going to use the basic ones today. So the next function in this category is the function random prime, which gives you a pseudo-random prime number in the given range. For example, you can find a random 10-digit prime by doing this: random prime 10 to the power of 9, 10 to the power of 10. Minimum value, maximum value. In this range, find a random number, a random prime number. The next function in this category is the function Mersenne prime exponent, which gives you the nth Mersenne prime exponent. So what is it? A Mersenne prime exponent is a prime number p for which the Mersenne number 2 to the power of p minus 1 is prime. For example, we can find the first 10 Mersenne prime exponents by doing this. We can find, this is the table of the first 10 Mersenne prime exponents. The next group of functions here is the sequence of primes. And here the most important function is the function prime pi. So that function gives the number of primes pi x less than or equal to x. And by the way, it has nothing to do with the number with the constant pi. It's just That's how we denote it. This is a very important function. We'll talk about this function again later, and this is just because the functions, some functions fall in, of course, they fall in more than one category here. So let's just start with the basics. Prime pi, you can compute the number of primes up to 10 to the power of 10 by just doing this. So there are this many prime numbers less than or equal to 10 to the power of 10. Or we can do some fun and we can generate a path based on the prime pi function. And here you go. This is the prime pi function from the values 1 to 1000. And this is a nice sort of visual stuff here in the Wolfram language. The next the next function is the zeta function, the function zeta, which gives the Riemann zeta function zs, which is defined like this. This is a complex valued function from analytic number theory. This is quite a there are some major and serious results, but let's not go there. Let's just play with it, and you have a function, of course, you want to plot it. So here we can plot it over the reals. We can plot the zx function over the subset of reals, or we can plot it over a subset of complexes. And yeah, this is what we get. Here we go. Some other functions in this category are z0, log integral, Riemann R, Riemann Siegel, Riemann zp, and other. So the next category is, again, a very important category of functions, primality testing. Prime Q is one of the functions, and as you can guess, prime Q is used to test whether an integer is a prime number or not. So, for example, we can test whether the number 119 is prime or not by just simply doing this, and false, it is not a prime number. Similarly, composite Q is used to test whether an integer is a composite number. So we can test whether 149 is composite or not by simply doing this, and this gives you false. So that's not a composite number, that's a prime number. The next one is the function coprime Q, which is used to test whether two numbers are relatively prime. So what are relatively prime numbers? Two integers are called relatively prime or mutually prime or coprime when the only positive integer that can be used to divide both of them is 1. So we can test whether 8 or 11 are coprime or not by simply doing this. And yes, they are coprime. So integers are relatively prime, of course, if their greatest common divisor is 1. There's a function for that. We have a function for that. We'll talk about it later, but here you can also, this is equivalent to this. Okay, so to their greatest common divisor being equal to 1. The next one, we already talked about Mersenne prime numbers, and the next function is Mersenne prime exponent Q, which is used to test whether an integer is a Mersenne prime exponent. So for example, we can test whether 5 is a Mersenne prime exponent by simply doing this. And yes, and we can check, do you remember the definition? So 2 to the power of 5 minus 1 will be 31, and 31 is a prime number, and that means that 5 is a Mersenne prime exponent. Or we can just do some nice sort of, again, some visual stuff. We can highlight Mersenne prime exponents here for numbers up to 100, and they're highlighted in red. Prime power Q is, again, as a basic function, which is used to test whether a number is a power of a prime number. So, for example, we can test whether 9 is a power of a prime number by simply doing this. And yes, 9 is a power, is 3 squared. It is a power of a prime number. Or we can write this really cool simple function to recognize Mersenne numbers. Because what is a Mersenne number, right? 2 to the power of n minus 1, that should be prime. And if we add 1 to it, that should be even 2 to the power of n. And that should be a power of a prime number. In this case, it should be a power of 2. So we can do this, and we can, using this, our simple function, we can check that this number that you see is a Mersenne number, whether this one is not a Mersenne number. Okay, and so the other subgroup, which is a bit different, is theorems and equations, which are not quite functions that are like prime pi, GCD, but these functions, we use them a lot if we want to compute something. Like, for example, primes. What is primes? It just represents the domain of prime numbers, and we can use it to test whether this number is prime or not by simply doing this. Does this belong to primes or not? The equivalent of it would be this one. Just checking, just using the function prime Q that we already talked about. Or there's a function reduce, and we can use it to reduce expressions over the primes, or we can use full simplify to simplify expressions assuming numbers are prime. For example, here we have this inequality, and we can find solutions to it, which are prime numbers. In this case, 2 and 2 are solutions. Or we can simplify an expression over the fields of primes. So we want to simplify this expression as assuming that P is a prime number. And this is actually a very, very famous result. That is called Wilson's theorem. You can read about it on the internet. This is a very famous result. And here you see that the symbolic capabilities in the Wolfram language are quite strong, really. Or we can use the function find instance, and that can be used to find solutions again over primes. For example, we want to find a prime number that is greater than 10 to the power of 10, and here is an instance of a prime number that is greater than 10 to the power of 10. So in this group, now let's go to factoring. We talked about primes. Now, what about factoring? The prime factorization of integers is one of the key notions in number theory. It says that every natural number can be written uniquely as a product of primes. And the unique factorization is needed to establish much of what comes later. It gives an alternative, conceptually simpler way to find a lot of numerical characteristics of a number. So let's again, here functions are grouped into the functions about factoring and the functions about factoring related functions. So factoring, of course, that's the most basic function is factor integer that gives you a list of the prime factors of an integer together with their exponents. So if we want to find the prime factors and the prime factorization of 120, we just do this. And here you go, 2 to the power of 3, 3 to the power of 1, 5 to the power of 1. And we can check by doing this simple thing, right? We can just multiply them and we get the number, and this representation is unique. We can even use this integer for computing for very large integers like this, and you see, we just very quickly get the result and look how big their prime factors are. So prime numbers are called sometimes the building blocks of integers. And why is it so? Because every integer is a prime or a product of primes. And here you can see that our machine just picks some random number and gives us the prime factorization of that number. And this representation is unique. Okay, so the next one is the integer exponent gives the highest power of p that divides n. We can use it in many different ways. For example, we can find the number of trailing zeros by doing this integer exponent and taken 10 as a b, and we get 4. Or we can just find powers of 2 in successive integers and get this nice plot, which gives, as I said, powers of 2 in successive integers, right? The next function I want to talk about is square-free q, which is used to test whether a number or a polynomial is square-free. For example, we can test that 10 is a square-free number, and we can check by doing this, because you see it's just equals 2 to the power of 1 times 5 to the power of 1. There are no squares here. Yes, and the next one, okay, let's go to the next group, which is factoring related functions. There are a lot of functions that come from the definition of prime factorization, very important functions. Let's talk about some of them. The prime nu, prime omega are the prime omega functions. The prime omega functions count the number of prime factors of a natural number n. For example, the small prime omega function, prime nu, counts the number of distinct primes of n. So if we have the following representation, the following prime factorization of n, then the prime nu will equal to m. So for example, we can use it to compute prime nu for 24, and we get 2. The big omega, the big prime omega, counts the total number of prime factors of n, taking into account their multiplicity. So again, if n has the following prime number representation, then the big omega n equals this one. And we can compute it again for 24, and we can check. We can just do factor integer 24, and you can see that all of these are derived from the notion, because 3 plus 1 is 4, and it has 2 different prime factors. And so the prime nu, the small prime, will be 2. It was 2. There's again a function Liouville lambda, which gives the Liouville function lambda n. A very important function, which is defined as follows, is if n has the following prime number representation, prime factorization, then the Liouville lambda n equals this. And as you can see, it only takes 2 values, -1 and 1. here is the table for all values from 1 to 10. And we can compute it. We can compute the Liouville function at 8. You see, it's -1, and we can plot it. Plot that sequence for the first 50 numbers, and you just get -1 and 1 values. Mangled lambda function is another one. It gives you the mangled function lambda n, which is defined as follows: if n is a power of a prime, then lambda n equals to log p, logarithm of p, and it is 0 otherwise. And so we can compute it at 25. And we can also plot the mangled lambda sequence for the first 100 numbers by just doing discrete plot, mangled lambda n 100. So another function is Mobius mu, which we will talk about that function later. So yeah, these were the most important, the basic functions in this category, factoring in primes. Next is again a very, very important notion, divisibility. The functions about divisibility and divisors. So divisibility is, one of the key notions in number theory. Let's just say give the definition quickly. So the number d divides the number n if there exists an integer k such that n equals d times k. So n is called a divisor, n is a divisor of d, and d is a multiple of n. And what are the functions that we use here? Of course, divisible, which gives you true if n is divisible by m and false otherwise. So we can test whether a number is divisible by 19 by simply doing this. And yeah, true, and we can check it. Of course, 437 divided by 19 is 23. Or we can do some symbolic stuff and see that this expression is always divisible by 15 when n is an odd integer, right? And we can check it for all the n up to 100. And yes, all the numbers are truly divisible by 15 here. Or we can just highlight numbers that are divisible by 3, and yeah, you get the numbers that are divisible by 3 are highlighted in red here. The next functions are GCD, LCM. Of course, the GCD gives the greatest common divisor of numbers, and LCM gives the least common multiple of numbers. So to find the GCD and the LCM of two numbers, you just do simply GCD for 18. So the greatest common divisor is 2, and the least common multiple in this case is 36. And a function that is really connected with this GCD LCM is the Euler-Tottian function, Euler phi, which, what does it give? It gives the number of positive integers up to some integer n that are relatively prime to n. For example, we can compute the Euler-Tottian function of 10 by simply doing this. And there's a great result. For any prime number p and natural number r, you get this. Yes, you get this equation, and again, we can assume that p is a prime number, r is an integer, and r is a positive integer, and we can expand this function, and we get this nice formula. Again, this shows how strong Wolfram language is in symbolic computations. And again, so other functions are extended GCD, Mobius mu, Jacobi symbol, Kronecker symbol that are in this category. Divisibility, and we talked about divisibility. Let's talk about divisors. As I said, p is a divisor of a if there exists an integer k such that a equals k times b. So what are the functions here? Divisors, of course, which gives a list of the integers that divide n. For example, the divisors of 1729, you just simply do this. Divisor 1729, you get a list of divisors. And you can here even check that, yes, all of them are divisible. All of them divide 1729. The function here, the next one is divisor sigma, which gives the divisor function sigma kn, which is the sum of the kth powers of the integers. So the sum of divisors of 20 is just divisor sum 120. The sum of squares of divisors of 20 is divisor sigma. You just write 2 here, 220, and you get this number. And we can even do this nice plot and compare the plots, compare the number of divisors, compare the sum of divisors, and the sum of squares of divisors. And divisor sum, it just represents the sum of form e for all e that divide n. It's basically a sum for all the divisors of a number, like this, right? For all the divisors of x. And we can use it to find the sum of squares of divisors of 20 by doing this 20, and then we just find the sum of squares of divisors. The other functions here are dedekind eta, elliptic theta, that you can sort of look later on your own. The next categories, congruences, and modular arithmetic. So this is a very broad subject. The congruences are of great practical importance in both number theory and everyday life. The theory of congruences was introduced by Gauss. He created a new branch of number theory by introducing a remarkable notation. Congruences satisfy a number of important properties and are extremely useful in many areas of number theory. And here you see the clock, the 12-hour clock, because modular arithmetic is sometimes called a clock arithmetic. That's because clock arithmetic is the modular arithmetic modular 2, and there's a very nice connection. So the functions here are mod, which gives the remainder on division of m by n. So compute 5 mod 3 by just doing this, or we can just plot the sequence with fixed modulus, by doing this. And of course, the values are only 0, 1, 2, 3, 4, 5, 6, and 7, because the modulus here is 8. Power mod is another important function, which is known as modular exponentiation. It just gives you a to the power of b mod m, like compute 10 to the power of t mod 3, easily by doing this. Power mod a minus 1m finds the modular inverse of a modulo m. Like in this case, we can find the modular inverse of 2 modulo 5 by doing this. And of course, we have a function for that is modular inverse. It gives the modular inverse of k modulo n. So we can compute the inverse of 3 modulo 5 by using that function, and we'll get 2. Or we can plot the sequence of a fixed modulus like this. Other functions here are multiplicative order, primitive root, Chinese remainder, power mod list, Carmichael lambda, primitive polynomial Q. Okay, so the next category is Diophantine and other equations, which is a huge subject in number theory. What is a Diophantine equation? It is a polynomial equation, usually in 2 or more unknowns, such that only the integer solutions are sought or studied. It's very difficult to solve a given Diophantine equation. It's not possible. So we just, say we solve a certain, like a given Diophantine equation. And so here we don't have the functions like a Diophantine equation, we can sort of, we can only manipulate on them using these functions like for example, integer, right? It just represents the domain of integers because our solutions, we want them to be integers. Like, for example, you can use it to check if the number of 7 is integer or not by simply doing this. Or you can use reduce, that we talked about it, to reduce expressions. For example, this is x squared plus y squared is 5 squared. That is a Diophantine equation, and we want to solve it over integers. And what do we get? We get results, 3 and 4, that's the solutions, and actually 3, 4, 5 are Pythagorean triples. So basically we just found a Pythagorean triple. Or we can use find instance to find solutions of Diophantine equations. Like in this case, this is 2 Diophantine equations, and we want to find their solutions over the integers. And the system just gives you this, this is an instance of a solution. As I said, Diophantine equations are a very broad subject. So what do? We narrow down, mathematicians narrow down the subject, and the simplest kind of Diophantine equation is the linear Diophantine equation. So a linear Diophantine equation in 2 variables is an equation of the form a times x plus b times y equals c, where a, b, c are integers, and the goal is to find the integer solutions x and y. It's very interesting to look at them geometrically. So geometrically, a linear Diophantine equation gives a line, and the solutions to the equation are the integer points that are on the line. And you see here in this nice example, you see that we just manipulate, we change the equation. You see the equation here above the plot. And we can zoom in, zoom out, and the red lines actually are the integer solutions here, right? This is a very nice, fun thing. The other functions are rationals, reals, algebraic primes. Okay, now let's talk about number representations. We talked about natural numbers, but there are many numbers, and there are many ways to represent numbers, and Wolfram is quite good at that. So let's begin with digit representations. And let's begin with the very basic function, integer digits. which gives a list of the decimal digits in the integer n, and integer digits nb gives a list of the base b digits in the integer n. So, for example, we can find digits in base 10, like doing this, or in base 2, by doing this, again, using the same function. From digits constructs an integer from a list of decimal digits. Like we can construct an integer, construct a number from its base 10 digits, and here you go. We can also use symbolic digits and base, you see? This is the base, and this is the symbolic digits. Base form is another function which prints with a number in expression given in base n. Like, for example, this is the number 33 in base 2, right? We can do a nice sort of table. We can do a nice table and see that expansions in different bases can be terminating or non-terminating for the same number. You know, we just change the bases, but the number is the same here. Number decompose is another function. It returns a list of coefficients of a decomposition of the number x in the bases, u, u1 to un. So, for example, we can decompose an amount of money, you see, in different denominations by doing this. And it returns a list of coefficients. Or we can decompose an amount of seconds in days, hours, minutes, and seconds by doing this. Other functions are real digits, integer reverse, integer part, integer name. So the next group here is about continued fractions and rational approximations. A continued fraction, what is it? It is an expression obtained through an iterative process of representing a number as the sum of its integer part and the reciprocal of another number, then writing this other number as the sum of its integer part and another reciprocal, and so on. And Wolfram language has highly efficient algorithms for finding large number of terms in continued fractions, as well as for handling exact continued fraction for quadratic irrationals. So let's start with the most important function, which is continued fraction. It generates a list of the first n terms in the continued fraction representation. Like we can, for example, let's find 20 terms in the continued fraction for pi, and this is it. Or we can find for terms in the continued fraction for a rational number, 47 over 17. And from continued fraction actually reconstructs a number from a list of continued fraction. For example, we just found these are the terms, and for using these terms, the function from continued fraction, it just recovers the number. Convergence is another function that gives a list of the convergence corresponding to the continued fraction terms. For example, we can find the convergence for a rational number by doing this. And you can actually see that the convergence actually tend to that number in this plot, right? This is the line is our number, is 272 over 105, and the convergence actually tend to the number. Now let's talk about hinging. This is the first constant, mathematical constant that we're going to talk about today. So far, we only talked about functions. So it's a mathematical constant, which is about 2.68545 and so on. And it is connected to these results that mathematician Alexander Hingin proved, which says that for almost all real numbers x, the terms ai of the continued fraction expansion of x have a finite geometric mean that is independent of the value of x, known as Hingin's constant. Basically, mathematically speaking, in mathematical terms, this is what he's saying. And here in this plot, the Hingin's plot is the red line, Hingin's constant is the red line, and you can see that this value, indeed, for almost all real numbers, tends to the red line. That is actually a mathematical term for almost all real numbers, but let's not go there. So let's just check for pi. Let's just check for log to the power of 5. You know, pi to the power of pi. Golden ratio. You see, it didn't work because we said for almost all real numbers. Square root of 2, it didn't work. P to the power of e, again, it works. Yeah. So other functions are rationalized, quadratic irrational q, continued fraction k. Okay, now let's continue this. A number of representations, and let's just talk about representing as sums of powers. There are actually two functions here I want to talk about. The one is squares r dn, which gives the number of ways to represent an integer n as a sum of d squares. For example, we can find a number of ways to represent 45 as the sum of squares by doing this. And you see there are 8 ways to represent 45 as the sum of squares. Or this function, power representations, nkp, which gives the distinct representations of the integer n as the sum of k non-negative pth integer powers. Like in this case, we can find representations of 1729 as the sum of 2 cubes by doing this. And you see that indeed, 1 to the power of 3 plus 12 to the power of 3 is 1729, so is this number. And actually, this is called a taxicab number. Very interesting numbers. 1729 is the smallest number that can be represented as a sum of 2 cubes in 2 different ways. And Ramanujan discovered these numbers. You can actually read about taxicab numbers. Another function here is elliptic theta. Now let's talk about partitions. Integer partitions, what does it do, this function? It gives a list of all possible ways to partition the integer n into smaller integers. Like, let's find all the partitions of 5. Yeah, these are all the partitions of 5. Partitions P gives the number Pn of unrestricted partitions of the integer n, while partitions Q gives the number Qn of partitions of the integer n into distinct parts. For example, partitions P for 20 is 627, and partitions Q for 20 is 64. Yeah. Okay, so these were sort of we talked about. We didn't so far talk about real difficult analytic stuff. And now let's talk a bit about analytic number theory. What is it? It is a branch of number theory that uses methods from mathematical analysis to solve problems about the integers. Analytic number theory can be split up into 2 major parts, divided more by the types of problems they attempt to solve than the fundamental differences in technique. And the 2 subgroups are multiplicative number theory and additive number theory. So let's just go into these subgroups now. So multiplicative, what is it? Multiplicative number theory. It is a subfield of analytic number theory that deals with prime numbers and with factorization and divisors. The focus is usually on developing approximate formulas for counting these objects in various contexts. So here the subgroups are zeta functions, Dirichlet series, arithmetic functions, prime numbers, perfect numbers, and some operations on them. And let's begin with zeta functions. Again, the Wolfram which supports zeta functions of a complex variable in full generality. One of the functions is zeta. We already talked about the zeta function. Let's now talk about the zeta zero function that represents the zero of the Riemann zeta function on the critical line. For example, using this function, we can visualize the first 10 zeros of the Riemann zeta function. Other functions you can see on your screen are zeta, Riemann equals theta, and the other functions. The next subgroup is Dirichlet series. So Dirichlet transform is one of the functions here, and it just gives the Dirichlet transform of expression with respect to n. The Dirichlet transform for a discrete function is given by this sort of formula. For example, for the Dirichlet transform here, 1ns is just zs, and the Dirichlet transform in this case is just the function, the special function polylog. Another function here is Dirichlet L. Arithmetic functions, let's talk about them. They're a very important subgroup, really. And what is it? An arithmetic function is any function fn whose domain is the positive integers and whose range is a subset of the complex numbers. For example, Mobius mu, we didn't talk about it. You know, this function was also in the category of factoring related functions, but now let's talk about it here. It gives the Mobius function mu n, which is defined as this. If we have the prime factorization of number n, and it is this, it has, then the Mobius function is defined as this, right? Minus 1 to the power of m if k1 equals to km, that is 1, and 0 otherwise. So now it takes 3 values, minus 1, 0, and 1. You can here see the table of the values. The other functions the other arithmetic functions are divisors, for example, we talked about it, divisor sigma, Euler phi, prime numbers. Okay, as I said, prime pi, we talked a bit about prime pi, but this is really what's interesting about it. Actually, this is how the whole subject of analytic number theory sort of got created because people wanted to find the estimates of the function prime pi, and here you can see in our screen that yes, the estimates of the prime pi are x over log x and log integral, and you can see that on your screen that they are really, the plot really shows that they're estimates. The other functions are prime u, prime omega, prime Liouville lambda, and Mandel's lambda. Now, let's talk about perfect numbers. We didn't have a chance to do it, but it's a very interesting thing in number theory. What is it? A perfect number gives the nth perfect number. That's the function in Mathematica and in the Wolfram language. And perfect number Q tests whether a number is perfect. So a perfect number is a positive integer that is equal to the sum of its positive divisors, excluding the number itself. For example, 28 is a perfect number because you can check. This is what I was talking about. This is the sum of its positive divisors, excluding the number itself, and it just equals 28. Here are the first 10 perfect numbers. We can even check them if they are perfect or not by using the function perfect number Q. Yes, they're perfect. And here is the plot of the length of the first 47 even perfect numbers with log-scale values. So you see that they are very rare, they grow very rapidly. And there's also a peculiar connection between perfect numbers and Mersenne primes. So the first one is, if p is a Mersenne prime exponent, then 2 to the power of p minus 1 times 2 to the power of p minus 1 is a perfect number. For example, 5 is a Mersenne prime exponent, and we can put 5 into this formula. And what does it say? It says that this number, 496, should be a perfect number. And yes, that is a perfect number. So the other way, every even perfect number has the form 2 to the power of p minus 1 times 2 to the power of p minus 1, where p is again a Mersenne prime exponent. So take this number and check that, yes, this is a perfect number. We can guess what p should be by using the function that we already talked about, integer exponent. So, okay, p really is p minus 1 should be like 6, so p should be 7, and we can check here. I think, yeah, there has been a typo, but that should be, oh, yes. Yeah, there you go. 2 to the power of 7 minus 1 times 2 to the power of 7 minus 1 gives you this number. And yes, 7, you can check, that is a Mersenne prime exponent. Here is the table of the first 8. You can compare Mersenne primes and corresponding perfect numbers. These are perfect numbers, and this is their corresponding Mersenne primes. And the other functions here are Mersenne prime exponent, Mersenne prime exponent Q. Now let's talk about operations. I mean, of course, because we deal with functions, all kind of complex functions, and there are some operations that are useful here, like sum, product, integrate, series, limit. We'll not talk about that because they are not purely number theoretic functions, but we can look with them. Yeah, they are very useful here. Additive number theory. So there was multiplicative number theory and there was additive number theory. What is it? Additive number theory is the subfield of number theory concerning the study of subsets of integers and their behavior under addition. So here the groups are integer partitions, base lab representations, representation in terms of powers, summation-related operations, arithmetic functions. We already talked about all of these functions. Let's not go there, but this is just to tell you what an additive number theory is and the functions there in the categories that the functions here are grouped into. Okay, algebraic number theory is another category in number theory. It's a branch in number theory, actually, that uses the techniques of abstract algebra to study the integers, rational numbers, and their generalizations. Here, the functions are grouped in these categories: algebraic numbers and representation. For example, right, what is this function? Algebraic number is an algebraic number represented in a particular field, right? We can represent an algebraic number by doing this. We can even do some arithmetic with it, and we can get a numerical approximation. The other functions are root approximant, minimal polynomial, and the other functions. So the algebraic number field, what is it? For example, one of the functions here is two-number field, which finds a common field or expresses numbers in a given field. For example, we can do this. We can express square root of 2 in the number field generated by this number. yeah, the other functions are number field integral basis, number field class number, and the others. Factorization, we talked about it. So here I want to talk about this Gaussian integers, which allows factorization over Gaussian integers, right? We can factor 36 over Gaussian integers by just adding this option, this method, right? Gaussian integers goes to true, and this, you see, you get -1 to the power of 1 times 1 plus I to the power of 4 times 3 squared. That should be 36 over that field. We can just, if we just say, okay, factor integer 36, it just gives you the factorization over natural numbers. The other functions here, the functions here are factor, integer, factor. And now, again, two sort of functions that we use in this category are extension, root reduce. Extension is a field extension for number theoretic and polynomial operations. For example, factor a polynomial over this field, and this is what you get, extension SQRT2. Or use root reduce, and that reduces an algebraic number to minimal root form. Yeah, like this. Another function here is two radicals. So yeah, this was it. A very sort of brief introduction to number theoretic capabilities in the Wolfram language. The notebook will be posted. You can look at it with all kind of links here, and you can. These all refer to some to the reference page of Mathematica, and you can just go there and read about all these functions in more detail. You can look at them at the examples. There are a lot of examples about all the functions. So the notebook will be posted. You'll get the links. And so what is next? What is next in number theory in our company? Of course, functionality, new functions, better performance. We're now working on writing courses and books about number theory using Wolfram language, where the stress is going to be just on number theory, and just Wolfram language is just the tool that we have. And of course, we always improve the documentation. Yeah, so let me just go to your questions real quick. Yeah, I think that was it. You can, again, there's a post in the Wolfram community page. You can ask your questions there, and we'll answer you.